Hi everyone! I wanted to discuss a new open source repository that Deepseek just released called DeepEP. Now, DeepEP contains a set of optimized NVIDIA GPU kernels, and one particular optimization that I found super interesting was a quote-unquote undocumented PTX instruction. So I'm going to discuss this and analyze this a little bit, and then I'm going to write this instruction and benchmark it on an H100. But before we get into that, let's have a really brief background on what CUDA is, what PTX is, and what SASS is. Now, at the very top level, you have CUDA, which is a programming language that's just an extension of C++, where developers can write code that's going to execute on GPUs. If you go one level below that, then you have PTX. And PTX stands for Parallel Thread Execution, and this is just a virtual instruction set architecture. You can kind of equate it to like WebAssembly or maybe Java bytecode. Now, there's actually one level even below PTX, even though PTX looks like assembly, called SASS. And SASS is going to be hardware specific. So this is going to target particular GPUs and execute directly on the hardware. Now, what happens during this is the NVIDIA compiler takes in CUDA code and compiles that down to PTX code. But the PTX code is still in the hardware agnostic phase. So there's an additional step that has to happen after that, where the PTX code is translated down to SASS code that targets a particular GPU architecture. Each GPU architecture has a different CUDA compute capability, which is different than the CUDA versions, so don't get those two mixed up because it's really easy to. The H100, for example, which is the Hopper architecture, runs CUDA compute capability 9.0. Now, the 4090, for example, even though it's a newer one, actually only runs CUDA compute capability 8.9 because it's consumer grade. Now, the instruction that Deepseek was targeting was one that was specifically accessing global memory, which is your VRAM. And each of those accesses can potentially take up to hundreds of clock cycles. So any kind of tiny speed up here is going to be super helpful. Now, on the NVIDIA GPUs, you have different hierarchies of memory still. At the very fastest access memory level, you have the L1 cache, which has the lowest latency, but it's also really small. On the H100, it's only 256 kilobytes. Now, one level above that, you have the L2 cache, which is significantly larger, but also takes a lot longer to access. And then, of course, at the very top, you have your VRAM, which is going to be very large, but take a really long time to access. Now, because PTX is a virtual instruction set architecture, you're not 100% guaranteed what SASS instructions are going to actually be generated. So what Deepseek is doing here is they're creating a highly customized PTX instruction that's a pretty good guarantee of a particular SASS instruction that's going to be generated that uses the cache in the specific way that they want. Now let's start getting our hands on the actual instructions. So here I am inside of the DeepEP GitHub repository, and if we want to find their customized PTX instruction, we can go over to the CSRC directory, and inside that the kernels directory, and come down to this utils.cuh. And .cuh is just a CUDA header file. And if we want to find the PTX instruction that's hard-coded inside of here, we can search for this 256B, because I know that's part of the instruction, and that'll bring us down directly to it. So let's kind of walk through what this is. First of all, if this extra flag here is not defined, it's going to use the actual optimized PTX instruction. Otherwise, it falls back to this very generalized instruction. You don't really need to worry about it, but it doesn't have any of the optimizations. So let's kind of walk through exactly what this custom instruction is doing bit by bit. First of all, we have this LD global, which is just loading data from global memory. And then the next portion of this NC, stands for non-coherent cache, which means that it's kind of bypassing any of the coherency mechanisms that the cache normally uses. Now, the next two portions are extremely important. First of all, we have this L1 no allocate. Now this means that it's not going to allocate any new data inside of the L1 cache. So any data that's currently existing inside of the L1 cache is going to remain intact and not actually be evicted. Now this second portion, L2 256B, means that it's going to be using the L2 cache, and it's going to be using 256 byte chunks at a time. Now you might be thinking, okay, cool, but what does that actually mean? So the main takeaway that you can get from this is that they're basically creating a hyper-specific customized instruction for their particular use case. So the non-coherent cache portion of this, maybe they have some read-only data that they're going to be accessing, so they don't need to have those normal coherency mechanisms. And then for the second portion, looking at the L1 and L2 specifications, let's say maybe they have a few different operations, and one operation needs to continuously, frequently access the L1 cache. So that's going to be really quick accesses back and forth. And then we have a second operation that's doing something completely different. Let's say maybe doing memory operations. This allows those two operations to not interfere with each other. So that second operation can keep moving around data without accidentally evicting that really important data that's stored inside of the L1 cache. So this allows that first operation to keep going really quickly since it's not constantly getting its data evicted and moved around. Now, before we get into the actual benchmarking portion of this, I want to touch on why I called this a quote-unquote undocumented instruction. So if we go over to the PTX instruction set architecture manual, which is just the reference provided by NVIDIA, we can look at all of the different components of this instruction. For example, we see this .L1 no allocate. That looks kind of familiar. We also see this .L2 256B, and we can find the LD global and other portions of this instruction documented inside of here. So pretty much what you can take away from this is all of the different components exist inside of the manual and are actually documented. The thing that's weird about this instruction is that these modifiers are not normally associated with the ld.global instruction. So I would say it's more of a customized instruction rather than an undocumented instruction. Now let's move on to creating our own simulation using this customized PTX instruction and benchmarking a couple different results to see if we can get and witness the speed up. So I'm going to move on to some CUDA code that I created, and this is just CUDA with some inline PTX instructions, just like they did in the Deepseek repository, and I will link to this code in the description of this video. So let's run through our scenario and see what's happening here. First of all, I'm going to have two different operations. One is going to be a standard load, and then another is going to be a specialized load. And they're going to be performing exactly the same thing, but the specialized load is going to utilize that customized PTX instruction. Now, in order to create a simulation where this could potentially speed something up, let's walk through what this is doing. First of all, I'm adding some dummy quote-unquote important data that's going to be frequently accessed, and this should be stored inside of the L1 cache. And since this is frequently accessed over and over again, we really want this data to remain intact. So we don't want this data to get evicted from the L1 cache if possible. Moving on to the next portion, let's say we have a secondary operation that's doing something completely different. Let's say it's streaming a very large amount of data. Well, we have a couple options here. In our standard load, we're not doing anything special, so the L1 cache data that we mentioned earlier might potentially get evicted in favor of this data since we're going through it. However, if we're doing the specialized load, we're going to use that customized PTX instruction to prevent us potentially evicting any of that data from the L1 cache. Now, this second streaming operation still has access to the L2 cache, which is still pretty quick, and it also has access to global memory, of course, if it needs it, but it should not be touching the L1 cache. And in order to verify that this has actually worked, so we can add something to benchmark here, at the very end, after all of this, we're going to go through and access that original data that should be stored intact inside of the L1 cache. Now, if we're using the regular instruction, not the optimized instruction, that data has potentially been kicked out of L1 cache into L2 cache, into global memory, who knows where. So theoretically, operations accessing that, aka these kinds of operations, could potentially be a lot slower since that data has potentially been moved farther away. So we're going to benchmark the two differences in between these, and we should see a pretty significant speed up. Now I'm going to open up my terminal that is connected to my machine with the H100, and I already have my cache benchmark code on here and compiled and ready to go. So all I need to do is do /cache benchmark, and that's going to execute our benchmark. And get ready, because this is going to execute really fast, because this GPU is really awesome. So let's let this go. And it's already done executing. So let's walk through what happened here. We ran through multiple different iterations for both of these different types of load. We have our standardized load, and we have our specialized load. And we can see the standard load took 0.158 milliseconds to execute, and then the specialized load took 0.148 milliseconds to execute. So this is actually 6.6% faster. So that is a 6.6% improvement. Now that might sound kind of small, but if you think about the use case that Deepseek has for this, and the amount of load that they have, and the amount of operations that they're running, this is going to be a huge improvement. So this kind of optimization is extremely impactful. Now, as a bonus, just for fun, let's try dumping the SAS code from our cache benchmarking binary. Now remember, the SAS code is going to be the hardware-specific instructions, whereas the PTX code was still hardware-agnostic. So I'm going to take my cache benchmark binary. What we can do is run coup obj dump, and then we'll do --dump SAS, and pass in our binary, and this is going to print out all of the instructions. So we can see here are all of our instructions. Oh, there's a lot right here. So what I'm going to do, let's grep that out. Let's do pipe grep 256B. That's my go-to, I think. And here we go. We can see the actual SAS instruction that was generated from that PTX code inside of the binary. So we can look at this. Here's the instruction, ldg.e.na.ltc256b.constant, and that corresponds to the PTX instruction. So they're kind of giving a hint to the compiler what instruction they want to generate. So if we compare this instruction that we actually see generated to the previous instruction that they mentioned inside of their repository, we can see, yes, it looks pretty similar, pretty much the same. So we did successfully get that instruction to be generated. Now, while I personally wouldn't call Deepseek's customized instruction an undocumented instruction, I still think it's really cool what they did and incredibly challenging. And I think if more people got into optimizing PTX instructions, that would be really good and potentially beneficial to society. If we had like some kind of bug bounty program for optimized PTX instructions, I think that could take us really far. So, thank you so much for watching, everyone. Lori Wired out.